Okay. The way this course used to be structured, today's lecture was the last lecture before the first exam. That is exam number 1.
Wow. Exam number 1?
What's that?
Exam number 1?
That'd be a
No,
doozy of
because
a...
it was in a different order. He changed the sequence of his book between whatever edition it was when I started
Man,
and
doozy
this class.
chaos.
So, all right.
Which order do you like better?
The old one. I don't like the new one.
Why don't you just...
But Shackelford doesn't listen to me. So, yeah. Okay, so we have.
Just like you don't listen to your students.
What's that?
I'm just kidding.
All right, so we've talked about TCT diagrams, the kinetics of thermal reactions. And last time talked about how we can use those to increase the hardness of a material, right, to make the material harder, right, creating different, the primary mechanism by which we make material harder is to create inhibitions to dislocation motion. And so you want the finer grained structure, the finer featured structure, the lamella, the smaller the lamella, the more, the harder it is, or the more randomly oriented the lamella, the harder it is. Right? Because the whole objective is to limit the ability of the dislocations to propagate. So now we're going to talk about ways we can do just the opposite, and that is to reduce the hardness. And we call the process of reducing hardness annealing. So this is heat treatment. To reduce hardness. Soften a material. So, as we talked about when we did the stress strain curve, right, something like this, we did the engineering stress strain curve, right? If this was the yield point for the original loading of the material, but we have done plastic deformation to the point where we've raised it up to this point on the curve, then for all subsequent loading, that essentially becomes the yield point, right? Because we have to go up here, we stretch it, we plastically deform it, and then we pull it back down. If I want to deform it more, I've got to go all the way back up there before I start deforming it again, right? So we've effectively hardened the material by increasing its strength. Right? It takes more load, we call it yield point problem. It takes more load to deform the material. So if I were trying to indent, right, remember the hardness was measured with an indenting tool. If I tried to put a little dent in here, I'm going to get a bigger dent on the surface with this material than I am with that material. Does that make sense?
But the material that's like the higher yield point would be more brittle, though.
It would have, yes, it would undergo less deformation before breaking. Yes. But the point is, this would be a harder material.
Yeah.
It has a higher strength, has a higher hardness.
Why?
Because I load up here and I unload here, right? Then to deform it further, I have to follow that load back up before I can go back on that curve.
I get that. What makes this says it's a stronger material because you get higher on the.
Because I can go to a higher stress before I deform it, right? Elastic deformation doesn't, we generally don't count elastic deformation, right? Hardness is a measure of plastic deformation, the permanent deformation, the dent that indenter leaves on the surface. Does that make sense?
Isn't the Y because it like messes up the internal structure? It makes it more random.
So what's actually happening is you've got a whole bunch of dislocations that have piled up in the thing, and so you can't propagate more dislocations because those dislocations that you've already created are inhibiting the propagation of further dislocations. They're straining the lattice to prevent you from being able to propagate more. So you have to go to an even higher load to get enough strain in the lattice to propagate past those. Does that make sense to everybody? Okay. This process of hardening we call cold work. So we're working it, we're deforming it, but we're deforming it while it's cold. Right? It's relative to the temperatures of, so we're not doing this at hundreds of degrees C or thousands of degrees C. We're doing this typically at room temperature. Okay, so it's cold work is relative to the temperature distribution of the material. It's cold, and we measure that cold work with a percent cold work. It's equal to the initial area, cross-sectional area, minus the final cross-sectional area, divided by the initial cross-sectional area. And then obviously times 100% if I want to get it in percentage. Because remember, as I pull on something, right, if I take a tensile sample and pull on it, as I deform it, the cross-sectional area gets smaller. Right? So it's, what percent of the initial cross-sectional area have I reduced? Percent cold work. I can have 200% cold work, right? If it's the right kind of material.
So it's just
Right? No, I can't have 2%. I take that back. No, I can't. No, that's a different thing. Sorry. So if I start off with something that's has a cross-sectional area of 10 square centimeters, and I end up with 3 square centimeters, right? It's neck down to 3 square centimeters, then that corresponds to 70% cold work.
Can you get them?
No. Right.
Oh, because they have
Yeah, it'll break at some point.
So if you break, you got 100% cold work.
No, because the cross-sectional area is still not 0. Right. So the percent cold work is measured that way, and we call that process strain hardening. Now, I didn't mention this last time with hardening because it was not something that we did in terms of heat treatment. Right, we weren't heat treating to get this. Last time we talked about all the hardening mechanisms we can do in terms of how we prepare the material to send it out the door. Because cold work hardens the material as well, makes it harder. We were talking about shop peening at one point sometime back earlier in the semester. What was I talking about shop peening? Where you bead blast, so you basically take a bunch of steel balls and you spray them with the sort of shot blast the surface.
I feel like it was mentioned in class.
Yeah, remember that in class?
Yeah, I'm trying to remember what it was, the context I was talking about though. Anyway, so if I can yes, give it. I can beat, if I take steel balls and just spray them at the surface at a high velocity, I will cold work the surface. So I will make the surface harder. So a shot blasted surface, right, will be harder because I've caused all this damage on the surface, and it makes it more resistant to scratching, for instance, other kind of surface damage. Okay. So cold work is usually what I'm trying to get rid of. If I want to soften this, maybe I had a part that I had to bend and contort and put it through a punch or whatever, run it through a die in order to get it into its final condition. Right, so you can imagine maybe I wanted to take a round bar and convert it into some kind of spoked structure. That is not a flower. Okay? Okay? You see what I'm saying? Well, I could run that through a bunch of dies. You know what I mean by a die? It's a hole with that shape.
Oh, like a press.
No, a die. It's a hole with
press
that
it
shape.
through a die.
So I have a bar,
Can
and I
you
push it
die?
through the hole. Right? Just jam it through the hole. And actually, if I were going from this shape to that shape, I'd probably have several successive dies. We'll talk more about die forming.
This
in a
would be a
minute.
good place
boy.
for a Play-Doh demonstration.
Yeah, fuzzy pumper barbershop. Exactly. Everybody know the fuzzy pumper barbershop? Seriously? Nobody knows about the fuzzy pumper barbershop?
The one I went
The fuzzy pumper barbershop. Okay, I guess that commercial predates you then. So the fuzzy
We're gonna
pumper
find
barbershop was no. You put Play-Doh in the thing and then you push it and it extrudes
Yeah,
through a die,
like-
right? Okay. So the idea here is maybe you have a die in between that kind of looks like this. Right? You see what I'm saying? And so you make it into this shape, and you take that and make it into that shape. Follow the process? Each time, you're cold working it. Right? You're shoving it through there, you're deforming it, and it gets it harder and harder and harder. So at this end, I've got a really hard material. It's in the shape I want, but it's really hard. Maybe I want to soften that up. I don't want it hard, I want it soft. So I've got, but I've put myself up here. How do I ever get back to here? So the process is annealing that gets it back. Right? So there's two kind of steps that I could go through for cold, to recover the cold. First is the recovery step. So this is at temperatures less than the recrystallization temperature. So if I look at my, microstructure, and so I've got these grains in the microstructure of whatever it is. I'm not going to worry about the structure of grains. When I've cold worked it, I've got dislocations that have piled up all in here. So I can't see them on a microscope, but if I could maybe etch it in some way so that all the grains would show up. Maybe I'd get a whole bunch of them, and there'd be a lot of them piled up at the grain boundaries especially. There'd just be damage all over the place in this material. You kind of get what I'm saying here?
If you were to.
There. So I've got all these dislocations that have piled up everywhere throughout the material. Okay. If I'm going to use a recovery annealing, a recovery mechanism, all I do is I heat it up to a temperature less than recrystallization. Okay, and then I'll explain in a minute where the recrystallization temperature is. But it's a temperature below that, so that I don't change the grains. All I do is I allow for thermal diffusion of all of these dislocations that have piled up. So I heat it high enough that there's enough atomic mobility for these things to basically, for the atoms to migrate out to the grain boundaries, regions, or to other dislocations, so that effectively I recover the structure of the material. Yes?
And this is, we're just heating, right? We're not doing
We're just heating it. We're just heating it to a temperature less than the recrystallization temperature is going to be on the order of 1/3 to 1/2 the melting temperature. Typically, it's just a ballpark kind of number. Okay. As long as you're using an absolute temperature scale.
So it just sort of fixes the lattice.
So it just allows the lattice to fix itself by atomic diffusion. I increase the temperature enough to increase the atomic mobility. Right, we talked about the Arrhenius behavior. Right, if I increase the temperature, then the things become more mobile, the diffusivity goes up. And I can just diffuse all of these extra atoms away into an unstrained condition. I relieve the strain in the lattice, because remember, if there's a dislocation, right, there's a dislocation in the lattice. Right? There's a dislocation in the lattice. There's a lot of tension down here at the bottom. The atoms are being pulled apart. And there's a lot of compression up here at the top. The atoms are being squeezed together. Right? So I want to relieve that. If I get enough temperature in here, enough high temperature, then this atom that's going to be pulled, that's sitting here, right, is going to be kind of squeezed out of that region, and I'm going to cause that dislocation. Then this one will be squeezed, and this will be squeezed. So I'll end up essentially obliterating the dislocation as the diffusion allows those atoms to move, kind of, okay? So, so that's recovery. So that's one process. The problem with recovery is it tends to be kind of slow. And it's still incomplete. It might get me back part of the way back down here, but it really never gets me back to completely, unless I wait a really long time. I'm not going to get back to here. I'm not going to get back to a pure virgin material. So the other option then is to go above recovery and actually allow recrystallization to occur. So temperature greater than T sub m over 3 to T sub m over 2. Depends on the nature of the problem, of the material. If I allow that, then what starts out, and I'm going to make my picture smaller so I don't have to draw so many grains. Okay, I start out with something like this. Those are all the, for lack of a better description, those are all the places where I have high strain because I've got these dislocations built up. What will happen in recrystallization is I'll start to grow new grains around each of those locations of high strain. So I'll relieve the strain by completely reorganizing the atoms in the vicinity of each of those defects.
So you basically semicircular.
Now, don't ignore the size.
You're just trying to create a grain boundary around.
Essentially, create a new grain in the vicinity. So you can imagine if I've got this dislocation and I have a bunch of them piled up, right? So I end up with this, and then here's another one that's piled up in there, and another one that's piled up, right? I end up with this really distorted lattice. This is a really high strain field. There's a lot of strain in that area. It's a lot easier for this thing if it's at a really high temperature for it to just say, I'm going to grow a new grain in here. And maybe that's the orientation of the lattice in that grain. I don't know, I'm just making stuff up. Yeah.
With the smaller grains, though, doesn't that prevent propagation of?
So the smaller grains, if they're really tiny grains, right, so it's a gradual process. So in other words, if I plot out then the hardness, rock wool hardness, for instance, as a function of the temperature, I get something that looks like this. Where this is the recrystallization temperature. Okay. If I get to higher and higher temperatures, then I get softer and softer materials because what effectively happens, and this is for a given amount of time, it's a fixed amount of time. Because what happens is these grains are allowed to grow. At a larger temperature, there's a bigger driving force for grain growth. So you're right. If I just start doing recrystallization immediately, or at the temperature just above it, I just get enough to grow smaller, slightly larger grains. Those slightly larger grains are only slightly more soft than the material was before with all the strain cold work in it. But if I go to a high enough temperature that those grains can then continue to grow, then I can actually get a softer material again. Or if I leave it at the lower temperature, the one just above recrystallization, but leave it for a long time, it's effectively the same thing. So if I do it just a little bit, then you're right, I end up with a bunch of small grains, and it's not nearly as soft as it was to begin with. But if I let it go a long time, what I effectively end up doing is erase all these things, right? So if I let it go longer, then each of these grains grows bigger until they run into each other. And I have a whole new grain pattern. Like that. Okay, so now, with additional time, all those little grains have grown together to form this.
This would still be harder than the original.
Which would still be harder than the original, yes. If, that is, the cold work was bad enough to be nice and uniformly distributed. So the increasing levels of cold work mean that I'm going to have smaller and smaller grains in my annealed piece. If I have more cold work, then there's more dots, and then I'm gonna have even smaller grains after annealing. So increasing levels of cold work can never, if I've got a really lot of cold work, I'm never gonna get back to as soft a material as I possibly could have, because the grain boundaries, there's still gonna be more grain boundaries. It's still gonna be fine-grained material, it's gonna be bainite instead of coarse pearlite kind of performance. It's still gonna be harder. It's not gonna be as hard as it was when it was cold work, but it'll still be harder than it could be if I let it regrow. But if I leave it there long enough, these grains will eat each other. Right? Or if I heat it and let it, if I let it grow, I'm trying to figure out, it's slower, if you get it to the right, it's a combination of temperature and time. Right? If I leave it there to a high enough temperature so that it can really grow and the grains will eat each other, or if I leave it for a long enough time, the grains will eventually eat each other. And they'll grow back to being full-size grains. Now, I'll come back to this other thing. Don't we forget to talk about the artwork. Okay. Artwork. So, again, the longer time is, so as T becomes greater than, as T increases, as the time at which the time that we spend above the recrystallization temperature, the ratio of grain boundary to volume decreases. Right? Again, if I just get it up there, I just grow a few little grains around all these spots, I got a whole bunch of grain boundary. As I leave it there longer, those grain boundaries will eat each other. Those grains will eat each other. One will grow, the other will shrink. And the grain boundary to volume ratio will decrease. And therefore it will get increasingly soft. Okay? But there's a limit. The bigger characteristic is getting rid of the strain hardening, because this is uniformly distributed throughout the whole matrix, the structure, the whole lattice. Getting rid of this is the big chunk. And so if I looked at hardness as a function of time instead of temperature, so this is hardness as a function of time, and this is assuming we're above the recrystallization temperature, it drops off. Right, that first bit, I get a dramatic drop in hardness. But as I leave it there longer and longer, I get diminishing returns as those grains grow bigger and bigger and bigger. Most of the hardness reduction, most of the annealing occurs in that initial period of time when I just recrystallize the material just enough to get rid of all the strain that's been induced by the cold work. Does that make sense? So, leaving it out here for additional time, and I've exaggerated, it might be more precipitous than this in the front end, but leaving it out here for this time is kind of pointless. It doesn't really get you anything. Once I've done the recrystallization and got that big fall off, that's the main point of annealing. The exception is, I don't know, I should try to see if I can find this. I tried it last time and I couldn't find it. Let me see if I can look it up. What the heck is his name? That's his brother's name. Let's see if that pulls it up. That's his. I can't remember his brother's name. This is. I can't
Google
remember.
Rob Hunt's brother.
Yeah.
Is it video? Is it video legal?
No, it's actual pictures.
Well, we got images.
And we can try, but I don't think that's going to get me where I want. That's Bob Pond himself. That's the senior. This guy's really cool. Yeah, I'm not seeing any of the pictures on here because I don't have the right number. It's his brother. I can't remember his
Press
brother.
volume recrystallization, right?
All right, nice guy.
No, I mean, you could just click that thing.
Oh, yeah.
I don't know if it'll change anything,
I asked him 2 years ago if he could send me pictures or copies of it, and he, you know, he sort of didn't respond. I mean, I talked to him a couple, you know, we went back and forth a couple times, and I couldn't get it. Okay, I'm not gonna get it.
If you Google Rob Pond's brother,
I don't think I can work at anything. Yeah.
Try something other than recrystallization. Is there any other adjective that you can use to describe it?
Okay, well, I'm not gonna get it, I don't think. See if I can figure out where this.
Thank you, Doc. Can I just ask, has everybody picked up a handout?
See if we. See if Bob.
Plated,
No. That guy's not Bob Pond. Who's Bob Pond?
is porosity.
Yeah, all right.
With metals.
Oh, this is his tie, though. This is.
Is that metal?
Yeah, his tie is made out of aluminum.
In the first floor, second floor, third floor, and I went up in the,
Actually,
This was back in your day.
And so, I'm going to ask the gentleman that's sitting all the way in the back, will you hold up your hand?
Is that you?
Now, you're my guinea pig. Now,
I was actually there for this lecture.
You were?
Yeah.
No, you weren't.
Yes, I was.
Are
Marilyn
you,
Hall.
wait, are you in that audience?
Oh, there you are.
Wait, are we looking for?
Where were you
No.
sitting down here?
No.
Well, you're
Yeah,
gonna
yeah.
blend in
Look for
real.
a shiny head.
You're gonna blend in quite
I
nicely.
had
in
hair at the
background.
time. I had hair
Oh,
at
darn
the
it.
time.
Was it white?
It was not white.
Good. Let's sit down a little bit.
why wouldn't you make this structure?
This guy's awesome. If you ever want to learn about this
Yeah, I
guy's,
want to ask you.
he's a phenomenal. He, I'm trying to see
But
if
we
any
never-
of these have, if he's got like, he doesn't do any, oh, whoa.
Or a dark spot that turns bright and shiny. I put my guinea pig up there. Can you tell it from there? Right. In each one of those little areas now, that's a crystal, right? That's one crystal. But you have to understand why you can see it.
Okay, he's not gonna do.
Was it his son that you were trying to find?
Rob Pond, yeah, his son, one of his sons, not, Rob Pond is the son who's a professor at Loyola, material
Skylar
science professor.
Pond, Stephen Pond, David Pond,
Richard.
Might
I'm
be
actually-
Richard,
I'm
might be
reading this.
Richard.
obituary.
What's that?
I'm reading his obituary.
Yeah.
I got morbid all of a sudden.
Yeah, you know you're going to depress me.
Well, it's got his siblings and his sons on here.
So it's Richard?
Robert Pond, Scott Pond, Stephen Pond, and Dr. David Pond.
Oh, Richard.
It could be Richard. I'm sure it could be here.
Anyway, okay, never mind. So here's the thing. I'll just explain it to you. So what his son did was he took this recrystallization process and combined it with his artistic skills. So one of his sons is an artist, and one of his sons was actually a material science professor, the one at Loyola. So what he would do is he would take a sheet of aluminum that was just sort of a basic sheet of aluminum, and he would go in and draw on the sheet of aluminum. Not with a scribe or anything, just draw like with a pencil or something. You know, so draw in a way that where you would damage, you would have lines on the aluminum. Right, some picture. Okay. So it would damage the aluminum, but you wouldn't see anything. Because all he had done was taken this, like a ballpoint pen without ink in it, and drawn on the aluminum. Okay. But locally, right where he drew the lines, you end up with severe damage. Right? You put a lot of dislocations into the material right there where you do the, and every place else is fine. And then he would take this aluminum, that you can't see anything, it's just like a sheet of aluminum, and recrystallize it, anneal it, and recrystallize it. And the grains would grow wherever he had put a mark on the sheet. But they would not grow, they would not initiate over here, they just stay there. And so these sections where he drew lines would grow new grains, and the places where he didn't draw lines would not grow grains. Then he would, come back and take that sheet, and where was the thing where he was holding the thing above his head?
That was somewhere in the middle, right?
Up here. No, it wasn't there. Student.
Try 2442.
Seriously? Oh, you're looking at this on your computer?
Yeah, just try 24.
See, if you had a log of wood, right, you wouldn't try to split it like this. You'd sit it up on the end and try to split it. Why? Because it splits easier, right? You said splits easier, I said it's anisotropic, right?
Okay, here's the thing. So you see that? So you guys have seen that on a garbage can, right? Metal garbage can, you can kind of see the like the little grains on it. You know what I'm talking about? Because those are actually zinc crystals that are grown on the top of steel. But you see them as individual crystals because they're big crystals, because the process in which they deposit it grows these big crystals. So this is the same thing. This is a chunk of aluminum in which he's annealed it slowly for a long time and allowed those grains to eat each other up. So now these grains, instead of being microscopic, are macroscopic. You can see the individual facets. It looks like facets. Reality, if I put my hand across there, it still feels smooth. Okay? But each of the grains is in a different orientation. So what you're seeing is the faceted structure of the, one of them, all of the atomic planes are like this. The other one, the atomic planes are like this. Another one, they're like this. Right? So you get all these different atomic planes at each of the different locations on there. And so you get different kind of refraction off the surface. So as a result, that looks like this cool granular pattern because you can see the grains. So what his son would do is he would do this, draw a picture, then put it in the furnace, grow the grains, let it grow long, stay in the furnace long so the grains would grow big, and then go out and take it out and etch it like that so you can see the individual grains. And in fact, the picture would suddenly appear in the grains of the aluminum. So instead of being this random speckly kind of thing, you'd actually have aluminum, the aluminum itself, the grains of the aluminum itself would be the picture.
Why don't you try annealed metal artwork instead of recrystallization artwork?
Okay, we'll try that.
Like a better shot.
Is that right? Annealed metal art, it's actually aluminum, but anyway. And I got it. No. I'll have to look it up. Maybe I can find it again if I spend some more time. But anyway, the point is, you can actually do creative things with this. Right? So this annealing process is not just about structure. In this case, it was about kind of this cool
So how do
visual
you
effect.
get the initial aluminum to be perfectly flat?
It's just an aluminum sheet. Doesn't have to be perfectly
Yeah,
flat.
but what if you got dinged somewhere along the way, and that would grow into its own crystal?
Oh, I see what you're saying. I see what you're
Like you
saying.
have to have a very flat.
So you have to have, yeah, he probably did some kind of an initial anneal on it to get rid of what was there, and then draw in more cold work so you can remove the initial cold work, put in some of your own, and then grow it again. Does that make sense? So anyway, but you can see that, and his tie is made out of the same thing. So every professor in the department had an aluminum tie that had been through this process, and so you can kind of see the specklediness of his tie. So he gave one to every professor in the department.
Did you have one?
No, I was not a professor in the
Well,
department, I
did you
was a
have-
student in the department, so I didn't get a tie. Okay. It's a soft point, sore point, but thank you for consulting. Anyway, so at graduation every year, when you get all dressed up in the gowns and everything, all the material science professors wore their aluminum tie with their gown. So it's kind of cool.
Did he die?
He's dead. When did he die?
Also a sore topic, just
When did he die, Cassidy? We were
He
looking
was 79.
No, it's not 79.
Are you sure?
He was.
I'm positive, oh, he was
No,
79.
he was 79 when he died.
Yes, but when did he die? How old?
He came back from the grave.
That would have been
2012.
So you could get his.
No, he was not 2012. He was not 79 in 2012. He was not 79 in 2012.
Could be a different Robert Pond.
Okay.
Maybe that was the issue.
Because Bob Pond there is, I mean, that would have been 24 years before that. He's not 55.
It looks like it might be 2007. At 89.
That I believe.
Yeah, okay. I
I'll
found
buy
another
that.
one.
Okay. This guy was a real character. Well, we're just blowing off stuff here. He built a tunnel under his house. So he had a house up on a hill out in the country, and he built a tunnel from his house out to his workshop so that he could do dangerous things out in the workshop and not blow up his house. But he still wanted the tunnel underneath the ground so that he could get out there in the wintertime. You know, he didn't have to walk across didn't have to walk outdoors. So he had an indoor shop for doing crazy stuff, but he had a tunnel out to it.
It wasn't claustrophobic. Were you over there?
Yeah.
You've been there?
Yeah. Okay. He's a really cool guy. This I should assign this as like inverted classroom required walk.
Please,
Can you take out one of the
Please, Dr. Gagner, don't.
Please don't do that. I hate it in word class.
Today we will be learning about moss petals.
What's an Amos?
Yeah, and it's in Amos, as in A-M-O-S, not A-M-U-S.
All the way it's written.
Who does not or will not see things as they are or wonder why things. So usually some old Amos, you know, who doesn't actually have any inquisitiveness to him. Anyway, one of his sayings.
Such amazing.
Okay, let's do a real problem. Recrystallization is a thermally activated process and as such can be characterized, at least for the first order, by the Arrhenius expression. As a first approximation, we can treat TR minus 1 as a rate, as the recrystallization time, as a rate. Okay, where TR is the time necessary to fully recrystallize the microstructure. For a 75% cold worked aluminum alloy, right, so 75%, we took a 1-inch thick alloy and we ran it through a press and rolled it down, or ran through a die, rolled it down to a 1/4 inch thick. Okay, so it's a pretty substantial amount of cold work. TR is 100 hours at 250 degrees C, and only 10 hours at 280 degrees C. So we're supposed to calculate the activation energy for this recrystallization process. How would we do
TR
that?
is time of recrystallization.
What's that?
Is TR the time of recrystallization? Am I correct in that? I just want to make sure.
Right over here. Where TR is the time necessary to fully recrystallize the material.
There you see it. When in doubt, annoy the professor.
That's right.
Dad.
When in doubt, ask a stupid question.
Out there was no such thing as stupid.
You're right, there's only stupid people, my bad. Okay. Okay, so what do? I want to find the activation
Solve for
energy.
Q.
What's that?
Solve for Q.
I'm solving for Q. How do I solve for Q?
Plug in what we know.
What's that?
Plug in what we know.
Plug in what we know.
Well, we know TR.
Okay, we know TR. What's TR?
Just TR.
100 hours.
Okay. We know TR. What else do we know? Come on, focus.
We know temperature is 250 degrees Celsius.
Okay.
And then we have a second TR.
We have a second TR.
It's the same temperature, right?
It's 10 hours, right? And temperature 2 is 280 degrees C.
And
Oh,
then
set
no
up
R's.
the bad one.
Yeah, we know R. Yeah, we know R. So, what do?
Take a ratio.
We take a ratio of what?
1 to the 1 TR to the other TR, so there's,
Okay, or 1 over
yeah.
TR1 divided by 1 over TR2 is equal to CE to the minus Q over RT1 divided by CE to the minus Q over RT2. C's cancel out, so we have TR2 over TR1 is equal to E to the minus Q over R times 1 over T1 minus 1 over T2. Right? And I didn't have to convert my times because I'm taking a ratio. So I can leave them in hours, that's fine. TR2 is 10, TR1 is 100, so that's 1/10 is equal to E to the minus Q over R times 1 over T1. What's T1? What's T1?
400,
No.
525.
523, correct. What is T2?
553.
553. Right? Okay. So you take the natural log of both sides, the E goes away. Left with minus Q of that is natural log of 110. So we have 1 over 553 minus 1 over 523 times the natural log of 110 times, no.
Should be 1 over.
Yeah, 1 over that, right. R, which is probably going to use 8.314 kilojoules per kilogram, divided by 1 over 553 minus 1 over 523. Does that make sense? Equals Q. So I just inverted the two terms. I don't have my solution. Huh. No, somebody else is going to have to find it.
So why is that 1 over 523 on the bottom?
So I have 1 over 523 minus 1 over 553.
Yeah.
I have a minus sign in front. So I switched the order with the minus sign, take away the minus sign.
But
So it's 1 over 553. What's that?
Because
I had to divide this into the other side.
it's, that whole thing is underneath. It's all being multiplied.
Here, I'll rewrite this if this makes sense. 1 over 553. Does that make sense?
I think it might be 71,305.
It might be 71,000.
According to
Yeah,
math.
you're sending the ones I
I got 184,557.
Somebody else do it. I have 2 people that agree before I can move on.
Did you say 184,000?
Yeah.
Yeah.
Okay, so what is it?
No, it's 42.
184.
56.
Huh?
184.56 times 10 to the 3.
0.56. This is in kilojoules per kilogram, or kilojoules per kilomole, or joules per mole. So we'll call it 1 kilojoules per
Let's just go
kilogram.
The actual number is 184,557.
Okay.
So it's,
So it would still be kilojoules. No. Because it's capital Q, it's not per mole, so it's kilojoules. Right. So it's kilojoules. It'd still be per kilomole, because it's ours in per kilomole.
Where did you get the temperatures?
I think that's it. Anyway, what's that?
Did you just get the temperatures?
These, but they're in C, so I just put them in absolute temperature, so Kelvin. Yes. Okay. Okay, so that's my Q. Now it's part B. Calculate the temperature at which complete recrystallization would occur for this aluminum alloy within 1 hour. basically I want to find, right, I measure the recrystallization time at two different temperatures. Find out the time it takes. Then I can estimate, well, how long do I have to, you know, or what temperature do I have to raise it to in order to get it to happen in 1 hour? So I can predict, you know, I can get this process moving along. So, how would I do that?
Do we need to find out what C is first?
Just do the same thing again, except with TR3 equals 1.
Right, so now I'm going to say, well, here, I'll start from this. TR3 divided by TR1 equals e to the minus q over r times 1 over T1 minus 1 over T3, and solve for T3. Because TR3 now is 1, TR1 is 100, so going back in here and sort of playing it out, I get the natural log of 1 over 100 times 8.314 divided by 184,557. Plus 1 over T1, which is 523, is equal to 1 over T3, I think. So what do I get there for T3? Does anybody get that?
184,557.
That's this.
Okay.
I'm doing it in joules because that's in joules per mole. This is down in joules per mole. Right. This is in joules per mole Kelvin. This is in joules per mole, so I end up with per kelvins plus per kelvins equals per kelvins.
I get 586.
586. T3 equals 586.7. So 587, which when I subtract the 273 is 314 degrees C. Now, it should have, I guess that's okay. Something seems a little wonky about that.
It's a shorter time,
Yeah, it should,
so it should be.
yeah, no, but it should, 250 to 280 was a power of 10. I would have expected 310 to be the final answer. Right, because we're traveling on a log scale. But maybe it's because it's 1 over t. Maybe that's the problem. It's 1 over, there's a 1 over t in there, an additional complication. But anyway, 314. Okay, so I will try to find pictures of the cool artwork. I'll initiate the conversation from 2 years ago, see if Rob Pond is still. I actually took classes from his son as well. I took classes from both.
The seniors side?
I took classes from Bob Pond Sr. He taught me my introductory material science. And from
Yeah, I'll be in all night. The only thing I gotta do is finish up that anatomy lab at 9:30, that's it. Okay. But I'll be around for as long as we need.
It looks like the annealing temperature, there's an example on the textbook, and as far as I can gather, the annealing temperature only depended on the melting point, the highest melting point of the substances.
Yeah, Blake.
Higher normalization. Because if you which differences if figure
so, figure 1031. That's a reference.
that's a figure of what we expect, but it also references.
1031, which is this one. No, let's see. Is indicated by 1031. That's because there they got the recrystallization temperature right out that graph. Right.
Right, because this is specifically for, yeah, for this element.
Okay, so. So, I'll have to remember, see if I do.
So you can find the mounting point.
So, I'm just trying to see if there was a, because I placed there, it was 2 years ago, so I don't know. I'll have to go back and revisit it, but is there a nickel copper question in here anywhere?
Not that I saw.
Let me make sure that I didn't. So if you go back to the nickel copper, what I'm trying to figure out is whether there's something that specifically said whether it should be in the 1/2 range or in the 1/3 range. You know what I'm saying? And I would have hoped there might have been some kind of a nickel copper example or something. Actually, let me check and see if the problem number is that. So milling. I'll have to go look at them.
Okay.
Oh, shoot. Sorry, Dana. Oops.